Hey everyone. Super excited to be here. This is my first Splash too, and I'm looking forward to talking to all of you. This work is about dealing with code duplication and reducing it, uh, and we built a tool to do that. This was done in collaboration with my classmates and Professor Izraelevitz, Razan, Kidus also at the back of the room. So let's get into it. Before I jump into the gory details, here's a super high-level overview of the entire talk. Library learning is a technique that automatically learns reusable abstractions from your code and tries to apply them as well. Prior work focuses on doing this for functional-like syntax, and we extend this to Python. So let's get into the details. Large code bases are prone to a lot of code duplication, and the same code is often written in different ways. This makes things hard to reuse. This makes it bug prone, and it's a source of technical debt. To deal with this, developers would typically extract common fragments of code. So if these are two duplicate-looking code, you extract it into some form of abstraction and replace them with a call to that abstraction. Library learning is a solution that automatically does this. It automatically learns these reusable abstractions and applies them on target sites. Library learning was kicked off by this work from Dreamcoded, which used it as a part of its program synthesis goal. It was something that it used in combination with its high-level program synthesis goal. However, these other two tools, Babel and Stitch, focused entirely on library learning. And Babel focused on the quality of the abstractions that it could generate, and Stitch focused on being fast and optimal. In our work, we built upon Stitch, so I'd like to take a look into how it works. So Stitch takes an input corpus of programs written in this lisp-like format. Down here on the right is some Python code or regular-looking syntax, and on the left is the input that Stitch accepts. It's a lisp-like syntax with the operator at the top of the list and all the arguments to the operator as the subsequent elements. So it takes this, it builds a tree, which looks quite similar to an AST to me, and it performs a top-down search to find optimal abstractions. One of the cool things about Stitch is that it can figure out abstractions where from different parts of the code where you have different variable names or slightly different structure. However, this doesn't generalize well to imperative programming languages like Python. And that's exactly where we come in. So we asked the question, can we extend Stitch to Python, and how can we do so? How can we port this tool that was built for lisp-like syntax to a more general language like Python? We focused on a subset of Python to make sure things work, and this is how Leroy is designed. It starts off with taking the input Python corpus and converts it into a Lisp-like format, which is what Stitch accepts. Then we pass the whole corpus of programs to Stitch, and we ask it to generate abstractions. And since Stitch doesn't know anything about Python, it generates many abstractions that don't make sense. And the rest of our pipeline deals with filtering those out and enhancing them so that the abstractions are valid Python functions. So that's what we do. We check if the abstractions are valid Python ASTs. We perform an analysis, and then we augment the abstractions to add some return variables and additional parameters if necessary. And then we finally validate the places where these abstractions were called to make sure that everything works. Let's take a look into how each of these steps work, starting with lispifying the Python corpus. So here's some very simple Python code, which just adds two numbers. And this is what its AST looks like. So we treat the AST as one very large function call, with the root of the AST as the name of the function, and all the child nodes in the AST are arguments to the function. And this allows us to very directly flatten out the AST into this Lispy format that Stitch accepts. And we repeat this process for every program in the corpus. Next, let's take a look at how we filter out invalid candidates from Stitch. Like I said before, Stitch doesn't know anything about Python, and so it generates many candidates which don't make sense. And we found two kinds of abstractions that are invalid in Python. One we call macro-like abstractions, and another one where it calls the abstraction incorrectly. So here's an example. This function looks odd, and it just adds. It doesn't even. It looks incomplete. It's an incomplete part of the Python AST. And here's the valid and complete part of the AST. So instead of adding two numbers, there's just a plus sign there with no right operand. And what Stitch intends us to do is to replace this 3 plus 1 with just a text for text replacement, and replace, put in the body of the function there. And that's why I call this a macro-like abstraction. This is clearly invalid, and this wouldn't work in Python. So we figure out that this is an incomplete part of the AST, and we prune this out. Next, let's take a look at another example where we have invalid parameters being called at the call site. So here's an example where the abstraction does something like X operator and a Z. And on the call site, what's intended to be done is to pass the addition operator as a parameter. This is again invalid in Python, and we figure this out and we prune it. Finally, we augment these abstractions coming from Stitch so that they're well-formed Python functions. To do this, we add additional parameters if necessary, and also add return variables as required. Let's take a look at how we add return variables. So if this is a function that is suggested, as you may look at this, this looks kind of odd. There's nothing being returned from this function, and if the variable X is being used somewhere in the code later, it's not going to be updated correctly. So we figure out exactly this. We figure out if X is being used somewhere later, and we return those values that are being created within the function. Finally, we validate the call sites at which these abstractions are applied, or intend to be applied at least. And then we figure out if they're correct or incorrect, and then we apply those abstractions accordingly. So let's look at another example. Here's an abstraction which just repeatedly prints a variable multiple times, prints its argument multiple times. And this is where it makes sense to apply this abstraction. So the variable X doesn't change ever within the loop, and passing it to the function passes it only once. and it makes sense to apply this. But here's another call site where we can't apply this abstraction. This is because the loop iterator I is continuously updated within the loop, and passing it once to the function at the beginning breaks the code because the value I needs to change continuously within the loop. So we perform an analysis and we figure out that such call sites are incorrect, and these abstractions can't be called here, and we prune these out as well. To evaluate Leroy, we used a corpus of 122 Python programs from a subset of the Python grammar that we work on. These programs were the entire set of unit tests for the compiler course at CU. On this corpus, we found that Leroy pruned thousands of abstractions. It pruned roughly 3,000 abstractions which were malformed part of the Python AST, and even more abstractions which were too small. Leroy pruned so many abstractions because every repeated part of the Python AST is something that every small part of the Python AST is repeated frequently. So think of the addition operator, the subtraction operator, and small things like this. They're very frequent throughout the code, and so it makes sense that the tool we use, Stitch, suggests that this is a common pattern. Finally, we found 6 valid abstractions, and they were applied to 2.5 call sites on average. We measured the size of the corpus before and after, and we were able to reduce the size by 4%. In the future, we plan to expand this evaluation to make it more comprehensive. Right now, we have a very small corpus of programs, and we'd like to extend the tool's capabilities to handle classes and lambdas and other stuff so that we can evaluate on a corpus from open source programs. Cool. So here's a summary of the entire work. And library learning is a thing that figures out how to compress your code and find reusable abstractions. And we built a tool called Leroy, which extends from functional-like syntax to Python. And here are some points for discussion that I'd like to bring up, notably how to expand this evaluation and where this tool can be applied and stuff like that. Thank you, and I'm happy to take questions.
All right, thanks for the talk. I can say coming up with 40,000 bad ideas and 6 good ones, just a day in the life for me. So I really empathize with this. All right, questions? Any from the audience?
I'm not sure. I'm curious if you would know the answer. Would this work be able to facilitate something akin to super compilation?
I am kind of not aware what super compilation is, so maybe you can help me.
Very vague oversimplification. I'm not super familiar with the field myself, but I believe it's something akin to where you would kind of like this, where you find abstractions repeated, the compiler would, and then based off of those, provide more optimizations because it's recognized the pattern.
Yep. This could be applied there. Yeah.
Other questions?
Hello, I have 2 questions. First, a low-level question. How long does it take to analyze a program? Because it sounds like you're going to look for any chunk of code, and that could possibly be abstracted.
Yeah, it takes a while. It takes about a minute for the 122 programs. But since this is something I think of as like a one-time thing, or it's not a continuous thing that needs to happen every second of every day. It's something that maybe you do in the code review process and then figure out that here's something that's duplicate and you could abstract it out.
Yeah, but if the cost is exponential in the size of the program, that's going to be tough if it's a big open source project.
Yeah, that's true. One of the reasons the cost is super high is because we didn't integrate super well with, we didn't tightly couple with Stitch. It suggests something and then we filter it out and then we go back in a loop. Instead, we could ingrain in their algorithm a bit stronger. Yeah.
Okay, and then the high level question is how to deal with imports and require cycles. So like I've seen lots of copies of insertion sort scattered throughout the Racket code base. And sometimes they have a function which has a name and it's like, well, this is a no-brainer, this should be in some library. And other times it's inlined in the body of the function. And it's like there's this block of code which is doing insertion sort. But a lot of times the reason that these different implementations exist is because it's not clear where to move them to, because you introduce an import cycle and that's not allowed in this language. So do you have any ideas about how to deal with this, or you think you should just work in a language that would handle these cycles for you automatically, or what to do?
Can you help me understand a bit more clearly?
If module A imports from module B, and module B imports from module A, then we have a compile error.
Yeah. I guess the way this the tool compresses, the way the tool converts it into a the Lispy thing, that's I don't think that Stitch internally knows anything about the intermodule dependencies, or so it's just looking for patterns of the code within the code.
Okay, so it sounds like filtering at the end might be a way to deal with this.
Yeah.
I'm guessing if you were to use one of these things in practice, you would like generate your abstractions, put them in like a utils library, and then just everyone would import that. That would be, but that itself would have no imports, is my guess. Maybe. Anyways, other questions?
Hi, thanks for the talk. So kind of focusing back on the human-centered aspects, which are kind of central to this workshop, I'm wondering what your thoughts are about how that relates to this work. And in particular, you're proposing this library of reusable abstractions, and it seems like there's a challenge in how do you expose that? How do you enable people to find them? How do you name them? How do you make them sort of practically reusable and not just existing in this library?
Yeah, that's a great question. We haven't thought too much about how to make this super interactive with people. I think one of the things that would be cool is like these abstractions, they don't come with names or anything interesting, like you said. That somewhere we could figure out with some human and put the human back in the loop and figure out what's a good name for these abstractions, or are these even worth it, and things like that. Sorry, I don't have a super good answer for that.
All right, any other questions?
Can you speak a little about the 6 abstractions that you ended up with? Like, were they meaningful to the tasks that were being performed?
Yeah, they kind of represented what was in the test suite. So the test suite had a lot of like integer manipulation, and it would do some if statement and then print something. So that was the kind of thing that got abstracted. I did start experimenting with this on like open source programs, and one of the things that kind of came up was like decorate, like it would suggest like abstracting a function which defines a function and does some computation in it, like a decorator kind of thing.
Anything else? All right, well, let's thank our speaker. And that concludes the morning session of HATRA. Thank you all for coming. And now, anything else to add, Michael, or should we just get